words with, kind. So he'd be going, he met the princess and he loved her because she was intelligent and kind and gentle. And I'd never say the word beautiful ever. So we're not going to say fair means good looking, because, you marry someone good looking, that's just asking for trouble, I think. Because you've selected them on weird criteria. So that has nothing to do with the things that are going to make you happy, presumably. Anyway, moving on. So I think the fairest prince in the land is the prince who, what? Is best at computer programming. Yeah. Is the busiest. Is the busiest prince in all the land. That's right. The busiest prince in the land. So she says, Dad, I found a guy, he's pretty damn busy. I've done all this blah, 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 and she gives me all these plausible reasons why he's the busiest prince in the whole land. Am I going to say, yes, you can marry him? Yep. No, I'm a dad. What am I going to say?
You're going to move to country.
You're going to move to a different country where there are fairer princes. No, I'm going to say, no, I said the fairest. When I said the fairest, I meant the fairest. So for you to be able to marry the fairest, you have to prove to me, beyond not reasonable doubt, you have to prove to me that he is the fairest. So when I'm saying your program is giving us the busiest beaver, I don't mean it's the best one I could find, or I had a fair guess at it, or it's faster than everyone else's in the course, or there's one of them, or there could be more of the same length, but there's one that takes the most time. I want you to find it. Now, it's very easy with small numbers and it's very hard with big numbers. So what I do not want, and what I'm frightened I'm going to get in this assignment, is a whole lot of people coming up with good guesses that look good. Can you see that's not an answer? That's not an answer to this question. If you have a guess that looks good, it's better come with a detailed mathematical proof showing that it has to be right. Either that, or you have to look at every possible one. They're your two options. Don't look at every possible one and have a detailed proof why you didn't have to look at every possible one, or look at every possible one. Because the problem when you optimize, like last year, I did a similar problem with someone, and they essentially had to find out, it wasn't an assignment, it was just a puzzle, and I liked it so much that I bought the company, and I thought we should have it as the assignment this semester. I said, find the one that prints out the longest string. And it was so much fun, it was awesomely good, but one person said, oh, I found a program that finds the one which prints the longest string, because I just searched through every possible program, and I look at how long each string each program generates is, and I found one that prints out a string of this length. And I said, that's pretty cool, except I found a string and it's longer. And the guy said, oh yeah, well, I did some optimizations. So don't do that. Does that make sense? Don't cut corners thinking, oh, I don't have to consider this case. It can't possibly be longer, better, busier, fatter, fairer, whatever. There's no way the girl in the kitchen wearing the rags could be the one that fits the slipper. I don't have to look at them. I only have to look at the girls in the good dresses. No, you have to look everywhere to be completely sure. Does that make sense? You're screwing up your face. It's a fairy story called Cinderella that my girls love completely, yeah, which is a really lame fairy story. But anyway, there you go. I mean, what criteria to select a wife on? Her shoe size. Insane. Okay. Shh. Are we ready to start the lecture? Did anyone have a question about task 2 that hasn't yet been released, but I've sort of told you what you've got to do already? So we could call it like task 1.9 or something. Yes? What's that? Yeah, you're time limited. Yeah. Details. What's that?
Where will it be released?
Oh, I'll do it. I will do it in lectures next week.
Oh, okay.
Yeah. What's that? Well, you've got to think about that. You've got to give me the correct answer. Shh. Oh, these are good questions. I should probably be answering them in front of everyone. So I'm nervous because I'm answering private questions. And it's an assignment you've all got to do. So let me just say, someone said, what was your question?
What do we submit?
What do you submit? You just submit a program that gets given a number and prints out the program.
Oh, okay.
So if I said 7 to your program, it prints out 7 bytes. Yep. Will we be testing your code? No, we'll just believe it's correct. You need to actually print out line underneath, I promise this really is the fairest prince in all the land. Dad. You're in. Okay. All right. I just wanted to finish off what we were talking about last time. We were looking at searching, we looked at searching on a table, searching on a list, searching in a tree. And I wanted to say a little bit more about searching in a tree. And then I wanted to talk about the last sort of interesting searching we're going to be doing for a while. There's some more searching coming later on. I've got a tree. That one's just too messy to use again, I think. But let's clear fellet. It's not completely gone, but it's stuffed up for all good purposes. Let's draw it like this. I've got a tree. It's got how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I want to search all the nodes. I'm going to have to do a sequential search on the tree. That means I'm going to have to visit every node. I can't be sure that what I want isn't in a node unless I've looked in that node, because it might just be hiding there. What are different strategies I could use to search a tree? This, I suppose, is not an ordered tree now, so looking at keys isn't giving me any clue. I haven't got be able to use comparisons. I can now only use equals. I can't use greater than and less than anymore. It's not a binary search tree, it's just a binary tree. Binary meaning forks 2 ways at most at every level. I want to have a systematic way of searching it. In an array, it's easy. You start at the beginning, you go till the end, and then you stop. Who said that? Is that the king? That's a quote from Alice in Wonderland. Maybe we could say well, I don't know. How would you do it? How would you do it? Yes?
You go all the way down one branch, then go back one node, go down another branch.
All right, you drive the car and I'll be the car. We start here? We have to, because I guess that's where we get into the tree.
Left, 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 left.
We're back where we started, after 4 lefts.
And then you go back one.
Up 1.
And then go down the other branch.
Down.
Then back 2.
Back up. Back up.
And then repeat the process.
Down. Down. Up. Down. Up. 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 Down. 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 Up. Down. Up. Up. Down. 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 Up. Up. I found out what the pipe bomb was. Okay, so this strategy of going down as far as you can on every search. Whenever faced with a choice, if this is a maze, we're always going down. And we only go back when we can't go any further down, and we go back as short a distance as we possibly can before we can go down again. So it's a strategy that really favours going down. Does anyone know what this strategy is called? A depth-first search. There are, of course, a million ways of searching these, different patterns of searching them. You've just got to make sure you visit them all. But a depth-first search is a very convenient one, because often your recursive programs naturally do this anyway, so it's easy to program a depth-first search. But what's another way of visiting this tree? Let's get someone else to say it. Okay? Someone else. Who's someone else? Put up your hand if you're someone else. I thought you were. No, you, shoot. Breadth first search. Let's do a breadth first search. Where do we search first? Here. All right, now where now? Then here. And do I go down now? Do I love going down? No. I hate going down. What do I do? Go back up. Search here. So I've searched all the top level, then all the second level. Where am I going now? I'm going to go back up and down, and I'm going to search here. And then I'm going to search here. Then I'm going to search here, and I'm going to search here. And notice to get from here to here is very annoying. It's like state transit, isn't it? Like the rail system. You have to go up, 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 up. That was how I used to get to school. Bus, train, bus. Or cross the road. And then last of all, we do this. This does layer at a time. It's called depth-first search. These are 2 systematic ways of sorting a tree, searching a tree, or visiting every node in a tree. Other ones, but these tend to be quite useful. They're good to have in your toolkit, because most most problems can be solved that involve tree searching can be solved reasonably well using 1 or 2 of those strategies. How would you implement these strategies, by the way? What's that? Yes, recursion does this one nicely. Implementing this is a bit harder. Maybe I won't do it now. Maybe we'll talk about it next lecture. Maybe that can be a puzzle for you guys to think about. Don't Google it. Are those guys, did they come back? No, okay. Don't Google it. Instead, try and work it out yourself. How could you write code to do a depth-first search of a binary tree? See how simple and pure and clean and nice and neat you can make your code. It isn't hard, so try and do it neatly. All right, so that's all I wanted to say about searching trees. Now, I had one other sort of searching thing to talk about in general, and it's this. I have, in fact, an example. A couple of years ago, a friend of mine gave me a puzzle. They knew I was going away for a weekend camping by myself. It was my birthday present. My wife said, "What would you like for your birthday?" And I said, "A weekend by myself." It was a horrible thing to say, wasn't it? But I was just really tired and stressed and overworked because of you guys. And I really just wanted to have some time to myself. And I hadn't relaxed for a long time. And she said, "Go for it." So I went camping in the most beautiful parts of the world. And I just spent a whole weekend by a stream, by myself. It was very nice. But I had planned to take with me a puzzle. And I love doing puzzles. And one of my girls' teachers said, "Oh, I've got an awesome puzzle from my dad, who's a mathematician." And she gave me this amazing interlocked puzzle. And she said, "Solve this puzzle." And it looked like this shape. Sadly, I forgot to take it with me, as I didn't realise till I got there. But I had some cardboard and bits of sticky tape and scissors, so I made a replica of it in the bush, trying to work out how it all worked. So can you see this shape? It's a series of hexagons and squares at the corners. And it's got lines. There's a line coming in each edge and leaving each edge. And there are three different colours for the lines. There are green lines, purple lines, and red lines. And then when I got this shape, it was all jumbled, and none of the lines joined up and anything like that. And the riddle was, can you rotate the edges such that all the green edges line up with green edges, and all the purple edges line up with purple edges, and all the red edges line up with red edges? And because I didn't have the puzzle, I couldn't do it. But I made this model and stared at it for a while, and I had my laptop with me, and I wrote a program to do it instead. That would solve the general case. And then when I came back, I just typed in the figures for that particular one, and it solved it for me. And it was very relaxing. It sounds weird, but there you go. So I would like, your homework this weekend is to get a tent. And how would I solve a problem? How could I configure? Can you see this is a search problem? The reason I'm sort of trying to show it now is I want you to see that a lot of interesting problems are search problems, but where you're searching is not on a tree or on a disk or in your data that's in your computer. You're searching sort of through virtual data that doesn't yet exist, data that's implied. So we call that the search space or the solution space. So the solution space for this problem is, well, each edge that's a hexagon can be in one of 6 configurations, and each edge that's a square can be in one of 4 configurations, and there are 6 squares, and there are 8 hexagons. So there are 6 to the 8. Did I get that right? How many hexagons are there? 8 hexagons. 8 to the 6 times 6 squares. No, what have I done wrong? 6 squares is 4 to the 6, 8 hexagons is 6 to the 8. I was right the first time. That's the number of configurations there are of this whole cube. So that's quite a big number. That's not too big. My computer can do that. So my search space is every possible configuration through rotation. And there's probably some symmetry in here. Probably if I got a solution, if I rotated everything through 180 degrees, I'll probably get the reverse solution or something the other way. I don't know. So I probably only have to search half that many things, but it doesn't matter. It's the same order of magnitude. So this is the size of the search space. So what strategy did I follow to search the search space? I could have used local properties like Minesweeper, but I instead decided the search space was so small that a simple sequential search would be good enough. So I just tried all the possible configurations one at a time. But let me show you precisely how I did it, because it's sort of interesting. I picked one of the nodes, say this one here, and I said that's my node number 1. And that can be in node number 1 can be in one of 6 possible configurations. It's in either configuration 1, 2, 3, 4, 5 or 6. Or maybe they call that node A. And then for each of those configurations, the square next to it can be in one of the square B. That can be in one of 4 configurations. And for each of those configurations, the hexagon next to that, call that number C, can be in 6. And what am I drawing? I'm drawing a tree. So it turns out that the solution space, one way of viewing the solution space, is it's structured a bit like a tree. It's not a search tree. It's not necessarily the fact that different configurations are related to each other in any way, though they might be. And if you study AI, you'll look at interesting ways of exploiting that. But I just wanted to do a sequential search through here. So what strategy did I follow? Do you think I did a depth-first search or a breadth-first search? It's an interesting question. Why would I do a depth-first search? What's the advantage of doing a depth-first search?
You need to find the final solution rather than you go to any possibility in the first or second level.
Can I I'll just pause on your answer rather than responding to it directly and say this. I've seen your hand. I'm going to go on some journey. And the solution's going to be at the very bottom of the tree, of course. A series of configurations. Every one of the nodes, every one of the faces is going to have to be in a configuration. So one of these states on the bottom is going to be the right one. And all I'm trying to decide is what order shall I visit them in. And because I'm lazy, I wanted to visit them in an order that was easy to program. And because I'm paranoid about being correct, I wanted to visit them in an order that's easy to program, because if my program's too clever and tricky, I'll probably miss something. And if I miss something, I'll lose the solution, and I have no intuition about what's going on. I won't be able to tell if I miss a solution. So I wanted a simple, short, simple program for all sorts of reasons. But also I didn't want to spend too long searching. So I didn't want it to be an inefficient algorithm. So they were the criteria that I was assessing when I was deciding what strategy did I want to adopt, whether I wanted to do a breadth-first or depth-first search. Now, you had something to say. Oh, I should have shut up. Say that again.
Solutions at the bottom of the tree, so you want to do it depth first, otherwise you keep searching across the breadth.
Oh, so certainly the solution's at the bottom. Whether that means I want to do a depth-first search or not, though, is still a moot point. Don't mix the word bottom and depth and think they're related, so hence one has to lead to the other. I mean, there's good reason to think it might, but there are also advantages to doing a breadth-first search. And I think this is so interesting. I might just leave this as an open question, and maybe this can be a chew question for next week, to try and work out whether for solving this problem, a breadth-first or a depth-first search would have been better or worse, and what are the advantages and disadvantages. And let's talk offline about that, because I'll let everyone think about that, because that's an interesting problem. Okay, so is that all I wanted to say? Oh, well, the last thing I wanted to say was this. That's right. It's come back to me occasionally in the lecture. Have you seen me screw up my face trying to remember something? There's been this elusive idea of something I wanted to mention about halfway through, and I keep forgetting to mention it, which is this notion that the solution space, the space you're searching to find your answer, isn't necessarily on a tape or in hard drive or something like that. It could be this virtual implied space that you have to search through, implied by the problem or something like that. The first example, and the really compelling example I ever encountered of that in my own life, was when I read about one of the early video game creators. And this was on the old bombing machines that had like 16 or 64K of memory. We couldn't believe how much memory that was. And someone wrote a game, and I can't remember the name of it, and I've been searching all day trying to find it. I think it was called Space Paranoids, but I could easily be wrong. Or Paranoid Androids? Oh, it's a song, isn't it? Yeah. That's my memory. See, it's jumping from, sometimes these are related. Points near each other actually have some relation between them. Here's how they did it. They programmed this game, and you went and colonized worlds, other worlds, and you landed on the worlds, and you'd go into a new galaxy, and there'd be a new solar, you're in the galaxy. You'd go to a new solar system, and there'd be a different configuration of planets, and good guys and bad guys and resources, and you'd explore this whole universe. And you could just jump from planet to planet to planet, and you could travel around as much as you wanted, and it was always different. But it wasn't randomly generated, because if you backtracked your steps, you'd go to the same places. But the number of places you could visit and the number of worlds just blew us away, because we knew, ourselves being programmers, there was no way they had enough memory to store all these different worlds. And, you know, everyone was having theories about how they were doing it, and the buzz was someone had estimated there were at least 1 million different worlds that you could visit, and it had 64K of memory. And when you went to one of these worlds, it knew exactly what the natives looked like and the characteristics of them, and it knew how much resources and gold and things and where the battleships were. It knew all this for every world. And that amount of information was just unbelievably big. And yet they were fitting it in 64K. And this is related now to, we're going back to Shannon and information. How could they fit that amount of information in such a small number of bits? Does anyone know how they did it? Or does anyone want to have a guess? What's that?
Compression?
A sort of compression, but it wasn't compression like I think you mean. They didn't have an algorithm. They didn't get all this data and then compress it down in some way and then cleverly unpack it as you needed it. But they did almost that, but in another way.
The state of each solar system was as affected by the one, like the next one? Or?
Each solar system was related to the other, so the information was distributed over them all. But nonetheless, even if they were related to each other, The amount of information, just
The solar system would generate the next one.
each one generated the next one.
Up or right or down each one.
How did it generate it?
What about if it was like a
Yeah.
random number
Yeah, it's coming out everywhere. Yes, 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 and yes, probably. What were you going to say? Yeah. Yeah, mathematical formula. They got the structure from maths. They didn't have to store the structure in the memory. The structure came from mathematics. That structure's already out there. We explore it ourselves. So they had some random number generator or some crazy hash function or something like that, that given the planet number, applied some crazy functions to it and generated all the other statistics from it. In a way compression, they compressed it all into one function. Does that make sense? And we just couldn't believe how clever that was. So in other words, the space we were exploring wasn't living in the RAM of the computer, wasn't stored in, or on the tape drive or hard drive or anything like that. It was in maths, and we were exploring maths space. And it was the closest I'd ever been to being inside maths. It was a very exciting idea. I'm not expressing it very well. But that's sort of what we do now when we write programs to solve problems like this. The space you're exploring doesn't exist inside the computer, but we can generate it and explore it as we generate it. Okay, so that's all I wanted to say about searching. Today's been our introduction to searching. Are there any questions about searching? No. Did anyone find the $2 coin? The $100 note. Oh. All right, let's take another pause, and this will be a real pause this time, and then we'll return. And the extension lecture today, if you want to hang around, you don't have to. Go home, rejoice, be happy. I'm going to show crazy, bizarre, weird things about C. So if you don't like C, go away. But I'm going to put up lines of code and I'm going to say, who can see what's wrong with this? And it's like a puzzle. And you'll stare at it and you won't see it and I'll tell you and you'll marvel and amaze. Okay.